Hello everyone. In this video I will solve in details with you AP chemistry worksheet about atomic structure and periodicity. It will be a little bit long video because I'm gonna solve the worksheet in details. I wish that you will get the benefit. Let us start. Number 1, a local station has a frequency of 98.6 megahertz. So this is the frequency. What is the wavelength of this station in centimeters? I want to find it in centimeter. In the formula that relates wavelength and frequency, lambda equal C over the frequency nu. Frequency should be in hertz, so I have to change the unit. 98.6 megahertz times 10 to power 6 hertz over 1 megahertz. So the frequency is 98.6 hertz. Now let me substitute. I want the lambda equals c speed of light, 3 times 10 to power 8 meter per second over 98 times 10 to power 6, sorry, here, okay, times 10 to power 6, and the final answer will be 3.04 meter. The question requires it in centimeters, so multiply by 100, it will be 304 centimeter. Number 2, which of the following types of radiation has the longest wavelength? In reality, number 2, 3, 4 are related to the electromagnetic radiation spectrum. So let me answer the questions referring to the spectrum. Number 2, which of the following types of radiation has the longest wavelength? In this spectrum, going from left to right, from left to right, we see that the lambda decreases, the frequency increases, correspondingly energy increases. So which of the following types has the longest wavelength? In number 2, we have options: gamma rays, visible ultraviolet, radar. So if we have to look here, we will see the radar has the longest lambda wavelength with respect to the rest that he mentioned. So the best answer is radar. Number 3, which of the following has the longest wavelength? Blue light, yellow light, red light, and green light. If we have to look here in the visible region, the one with the longest wavelength goes for red. So the answer is red light. Which of the following types of radiation has the highest energy? So I will pick up the one with the highest frequency. The highest frequency corresponds to highest energy. We will see gamma rays. So the best option here, gamma rays. Number 5, if the wavelength of ultraviolet light is 125 nanometer, what is the energy of 1 quantum? So let us see. E equal H nu equal Hc over lambda. H goes for the Planck constant, 6.626 times 10 negative 34 c speed of light, and the lambda which is 125 nanometer, that corresponds 125 times 10 to power negative 9 meter, because here in this formula lambda should be in meter. So the final answer in up to 3 significant figures, 1.59 times 10 negative 18 joule. For a neutron with mass 1.675 times 10 negative 27 moving with a velocity 4.20, what is the de Broglie wavelength in nanometer? Formula for de Broglie, lambda equal H over mv. H goes for Planck constant. So Planck's constant, and the mass in kilogram is 1.675 times 10 negative 27 multiplied by the velocity 4.20. So mass here should be in kilogram. So the final answer up to 3 significant figures, 9.42 times 10 negative 8 meter. That corresponds to 9.42. You multiply by 10 to the power of 9 times 10 nanometer. Which of the following electronic transitions in a hydrogen atom would have the longest wavelength? Here he's giving me options 4 to 1, 4 to 2, 2 to 1, 4 to 3. If I have to draw the energy levels, this is the first one. Usually there is a huge difference between energy level 1 and energy level 2, and as the energy levels increase, they become closer and closer to each other until they form a continuum. Okay, what are the transitions? N equal 4 to N equal 1, this is the first one. N equal 4 to N equal 2, the second one. N2 to N1, third one. And N4 to N3. The one with the longest wavelength goes the one with the lowest energy difference, which is the transition from N equal 4 to N equal 3, and this is the best answer. Number 8, which of the following of electronic transitions would have the highest energy? So this is exactly the opposite. The one with the highest energy transition goes, as you see from the chart, from N equal 4 to N equal 1. So part A is the first answer. Sorry, excuse me. Okay, number 9. Calculate the energy change resulting when an electron moves in a transition from N equals 6 to N equal 1. From N equals 6, which means this is an initial, N equal 1, this is an final. I want to find the energy change, so the formula delta E equal minus 2.178 times 10 negative 18 1 over N square final minus 1 over N square initial, which is minus 2.178 times 10 negative 18, 1 over 1 minus 1 over 36, and the final answer is minus 2.118 times 10 negative 18 joule. And the minus is expected because here there is electromagnetic radiation emission, because the electron is moving from high energy level to low energy level. Number 10, calculate the wavelength resulting from the electron transition from N equal 4 to N equal 1. First of all, let me find the energy corresponds to it. Minus 2.178 times 10 negative 18, 1 over 1, which is the final, and that will be the initial, minus 1 over 16. So the final answer is minus 2 for energy, up to 4 significant figures times 10 negative 18 joule. I want to find the lambda. Definitely I will not use the negative in energy, because the negative has a physical meaning, as we said. When electron goes or moves from high energy to low energy, radiation will be released, and the lambda should be in positive sign. So delta E equal hc over lambda, Planck constant. So let me substitute 2.042 times 10 negative 18, Planck's constant 6.626 times 10 negative 34, speed of light 3 times 10 to power of 8, all divided by lambda. And the final answer up to 4 significant figures, 9.735 times 10 to power 8 meter. Now match the following series in the hydrogen atom with the appropriate transitions. As you see here in this figure, we have Lyman series that lies in the ultraviolet rays region, Balmer visible, Paschen infrared. Okay, let us match it. From a higher energy level to N equal 1, so the series from high energy level, as you see here in the Lyman, 2 down to energy level 1 goes for Lyman. From a higher energy level to N equal 2 goes for Balmer series. As you see here, goes for to energy level 2 goes for Balmer. From a higher energy goes for Paschen series, this one. Ultraviolet region goes for Lyman series, infrared goes for Paschen series, and visible region goes for Balmer series. When an atom at its lowest energy state, we say that it is in the ground state. Ground state. When an atom has absorbed energy, we say that the atom got excited. Define paramagnetic and diamagnetic. Look here. Paramagnetic atoms with unpaired electrons, we call them paramagnetic. Paramagnetic atoms are attracted to magnet, while atoms with paired electrons, we call them diamagnetic, and they are repelled by magnet. Number 15, consider only the following quantum levels for the hydrogen. Draw all of the emission lines possible in the above electron diagram. Let us start drawing the lines possible from n equal 5 down to n equal 1, n equal 4 to 1, n equal 3 to 1, 2 to 1. Other possible emissions from n equal 5 to n equal 2, then to n equal 3, then to n equal 4, from n equal, and then from n equal 4, and then from n equal, from n equal 5 to n equal 2, and then this one from n equal, excuse me a little bit, we'll repeat, from n equal 5 to n equal 2, n equal 4 to n equal 2, and n equal 3 to n equal 2. This is the second possible. And then another series that's possible from n equal 5 to n equal 3, then n equal 4 to n equal 3, and the last one, which is possible, from n equal 5 to n equal 4. How many emission lines are possible if we have to add them? 4, 3, 7, 9, and 10. We'll continue. Photons of the highest frequency will be emitted during what transition? Highest frequency corresponds to the highest energy difference. If we have to take a look on the chart in the diagram, let us see which one has the highest energy. It is from n equal 5, high energy difference, from n equal 5 to n equal 1. So n equal 5 to n equal 1. Longest wavelength corresponds to the lowest delta E from the chart, the lowest delta E, as we see from n equal 5, this one, to n equal 4. You will tell me why n equal 3 to n 2 or 2 to 1, because as we said, as they go up, the energy difference decreases until they form a continuum. So this is n equal 5 to n equal 4. According to Heisenberg uncertainty, if one attempts simultaneously to measure the position and momentum of the electron, the more exactly the position is measured, the greater will be the what in the momentum. Momentum is simply the mass times velocity. And according to Heisenberg, the more we know about the position of the electron, the less we know about its velocity. So the best answer, there will be occurring an error. What is the maximum number of electrons that can be placed in a single orbital? So single orbital can hold maximum 2 of electrons. Which of the following is P block? Then asking a 19D block. In the periodic table, these we call them S block. These we call them S block. And this P block. Transition elements D block. Inner transitions F block. Okay, so which of the following P block? The one that as I can see among the options he gave, copper, chromium, chlorine, sodium, the option is chlorine in the P block. Which of the following is a D block element? The one that I see from the options that he has given me is the chromium. And which, now give the electron configuration, abbreviated one, and orbital notation of selenium. Selenium with atomic number 34, according to the electron configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Now the abbreviated one, abbreviated electron configuration. So 10, 18, this is argon, so I can replace it by argon, and the continuation 4s2, 3d10, 4p4. Orbitals, it means when I draw the electrons. So this is 2 electron, p6 in 3 different orbitals. Each orbital holds as a maximum of 2 electrons, 3s2. Okay, you can continue the rest. Now, give the rare gas notation for iodine. If I have to, I will solve number 21 because 22, 23 is similar to 21. Okay, so for iodine, the atomic number 53, its electron configuration, the normal one, the regular, normal, or regular electron configuration is krypton 5s2, 4d10, 5p5. This is the normal one. So the rare electron configuration is that when I arrange from the lowest to the higher as per energy levels, which is not normal. This is not what we do. So krypton 4d10, so we will write 4 and then 5s2, then 5p5. This is a rare one. How many unpaired electrons are in the orbital notation for the nickel atom? Atomic number for nickel is 28. Let us configure 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Okay, so let me see how many unpaired in the last one, highest one. Sorry. Okay, so okay, so excuse me for the inconvenience. Okay, so we start. So for the nickel, as we said that we have 28, and the configuration 1s2, 2s2, 2p6, 3s2, 3s2, 3p6, 4s2, 3d8. So if I want to count for the unpaired electrons, I'm gonna draw this one. 1, 2, 3, 4, 5, 6, 7, 8. So I'm left with 2 unpaired electrons. Now, what about how many unpaired for Fe3 plus ion? First of all, let me configure Fe, then we will configure Fe3 plus. So Fe is 26. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. If I want to remove 3 electrons, 3 plus, I will start removing from the highest energy level. So from here, I will move 2 and here 1, so left with 5. So how many unpaired electrons? This is 5. 1, 2, 3, 4, and the answer is 5. Which of the following ions is diamagnetic? As we said, diamagnetic, it means having paired electrons. After you try all, Mg2 plus will be the answer. Why? I will explain. Mg12 2 plus configuration 1s2 2s2 2p6. So as you see here in that energy level, all of the electrons for p paired. So the best answer is Mg2 plus. Number 27, which of the following diamagnetic, as we said, which of the following, it has 3 unpaired, which of the following is paramagnetic? Paramagnetic, it means that there exists unpaired electron. Again, after you do what you have to do, the option that it's given, the correct one will be when it is +2 ions. So you have to configure it when it is +2. So which of the has 3 unpaired when it is +2? The option, it will be cobalt. I explained for you how you do the electron configuration. Number 29, which of the following best describes the variation of atomic radii of elements with respect to position on the periodic table? Learn, please, that the atomic radius increases across the period and decreases across the period and increases down the group. The energy needed to remove an electron from an atom in the gas phase, we call it ionization energy. Which of the following groups of elements arranged correctly in order of increasing first ionization? Okay, ionization, it's the energy needed to remove electrons from a gaseous atom. The trend of ionization energy is that ionization energy increases across the period and decreases down the group. So based on the definition, the best option is B. List the following elements in order of increasing affinity for electrons. I have these elements. First of all, what's affinity for electron? An electron affinity is defined as the amount of energy released when an electron is added to the outermost. The trend in the periodic table, trend in the periodic table is electron affinity increases across the period and electron affinity decreases down the group. Okay, based on this, we can, using the periodic table, the option or the arrangement will be chlorine less than sulfur, less than aluminium, and less than magnesium. Increasing order, it means that sulfur greater than chlorine, and so on. List the above elements in order of decreasing atomic radii. As atomic radii, as we said, decreases across the period and increases down the group. So it will be exactly the opposite of this arrangement. So magnesium greater than aluminium, greater than sulfur, greater than chlorine. Which of the following elements would have the greatest difference between the first and second ionization energy? Between the first and second ionization energy, I always choose elements of group 1. Why? Because between them we will be taking electron from a stable ion that has the same electron configuration as the noble gas. Lithium in the gaseous state, the first ionization energy, lithium plus electron. This is the first ionization energy. Then the second one, as you see, we are removing electron from a stable ion. from a stable ion. Lithium is a stable ion that has the same electron configuration as the corresponding noble gas, which means that we need a lot of energy. So option goes for group 1. Which of the following is expected to have the largest radius? Okay, first of all, let me write the atomic numbers. Phosphorus 15, here sulfur 2 minus, okay, 15, 16. Okay, here number of electrons 18, 3 minus 16 and 2 electrons, 18 electron. This is 15 electron, and this is 16 electron. Okay, I want to choose the one with the largest radius, which contains the largest number of electrons. I have two options with the largest number of electrons, so I have to look at the nuclear charge. This has 16 in nuclear charge, this is 15, and the 16 protons attract more than 15 protons, which make it smaller in radius, so the option goes for part A. This was 34 questions solved for you. Part 1, we will continue